our presenter can address your question at the end. So Joseph, I can see your screen. You want to test your audio?
Hello?
Hello, we can hear you. Wonderful.
Hi, Sarah, this is Joe.
Great. Well, you sound good and I can see your screen, so I'm going to let you go ahead and take it away.
Okay, sounds good. Thanks. Righty here. This looks good. Okay. Hello, everybody. Welcome to my virtual hydrology days talk. My name is Joseph Pugh, and I'm going to be speaking on quantifying uncertainty in the measurement of turbulent flows with the goal to enhance water resource management. And I'm a first-year master's student at CSU. I'm part of the Environmental Fluid Mechanics Laboratory under the direction of Dr. Karan Benagamurthy, and my co-advisor is Dr. Tim Gates. So that's sort of my research specialization. And then within the master's program, I'm also involved in the Water and International Development track, which sort of pairs a study of engineering principles with sort of an anthropology lens of community empowerment and resiliency, and how to transfer some of this knowledge and incorporate it in sort of a development context. So that's sort of where I'm coming from. I started off with an undergraduate from a small liberal arts school in Minnesota, a BA in biology and math. And then sort of decided halfway through there I wanted to do an engineering track, and ended up at CSU. That's where I am in 2020. So the scope of my research is essentially it's funded by a grant from the USDA that aims to quantify the uncertainty and the lack of accuracy in the way we measure flow in open channels, especially in an irrigation context, and especially in a irrigation context where the systems are located in water scarce areas throughout the US. So in Colorado, we work primarily in the Arkansas River Valley, down in Rocky Ford, Colorado. CSU has an extension center down there where we base a lot of our field work out of. Essentially, what our goal is to improve the efficiency of irrigation systems, and sort of the part I play in that is looking at how accurate we can make the ways we measure the flow rate through these canals, because flow rate measurements are very critical for understanding just the total mass, the volume of water that is moving through these systems at any given time, how to delegate that water to different farmers, and so on. And this is important because irrigation is a very consumptive water use. It's regarded as the most consumptive water use actually globally. That was written in 2003, and is considered to be held true. And you know, this issue is becoming even more and more important because, as we very well know, with increasing issues due to climate change, there's going to be more issues due to water scarcity. I have this little infographic here from the UN showing that a lot of the world's population is going to be at risk to water scarcity issues. And on top of that, we have growing population numbers, so this kind of exacerbates the problem. So that's why we sort of need more efficient systems. We want to be using the water that we have in the most efficient way possible. And the way one way we can do that is measure it more accurately. So like I mentioned before, the current standard protocol for measuring the flow rate in an open channel, in an irrigation channel, really in any open channel. This is used to calibrate hydraulic structures and measure flow rates in rivers. They use these types of devices on anywhere from somewhere as wide as the Mississippi River to a 10-meter wide canal, like we've worked on in southeastern Colorado here with this ADCP. So there's two devices I'll kind of talk about here that use acoustic Doppler technology. The first is the ADV, the Acoustic Doppler Velocimeter. This just offers a point measurement of velocity. So you essentially need to take several different measurements at different depths along starting within a canal in order to establish a velocity profile. And then we have the Acoustic Doppler Current Profiler, which is shown on the right here, which allows us to sort of integrate over the entire canal at several different points to find what the mean velocity is at each of those at each point in the canal, and that integrating across the entire canal allows us to establish a volumetric flow rate. So there are certainly some limitations when using these devices. I'll go back just one slide here. You can see with this graphic provided by Sontech, which is one of the manufacturers of the ADV, is that this person here is actually standing within the stream in using the ADV to measure a velocity point here. So one of the major limitations to using these devices is what we call the intrusivity of the instrument into the flow. Essentially, this just comes from the principle that whenever we place a probe or a measurement device within the flow, that obstruction to the flow actually propagates upstream and changes the entire nature of the flow in a way that you can't really parse apart between what the velocity measurement is reading and what it would be without that intrusive element present. And with the ADCP, there's also some blanking zones that are well known. This image is from a paper by Simpson, 2002. Essentially, what limits the ADCP is that there are just some distances within the stream that just can't be directly measured. So from the water surface down to the length of what's called the transducer, which is the part of the probe that emits the acoustic signal, and then there's also an additional blanking distance. The ADCP actually has to extrapolate what the velocity measurement is reading in this area, and that introduces some problems due to the fact that extrapolation is inherently problematic, especially when the code used by the ADCP doesn't fully represent what the actual conditions in the field are. So the whole purpose of using these devices is to calibrate hydraulic structures. So I have a rating equation here where essentially the Q is what we're trying to determine, and what the hydraulic structure allows us to do is find the height of the stage, the water level above a structure such as a weir, and relate that to this Q here, this flow rate. So we wanted to try to determine flow rate. And the way these hydraulic structures are often calibrated is using the ADCP. So what we're essentially trying to do is blend together three elements of data collection. So I'm working with a student, another master's student named Joey Sinclair, whose specialization is in computational fluid dynamics, and we're sort of pairing together three realms of data. So we're working in the field, we're collecting data from the field. We're also modeling hydraulic structures in the laboratory and using the flumes we have in our lab to collect data. And we're also modeling those hydraulic structures within software such as Flow3D to produce models as well. And essentially what we want to do is develop rating equations for all three of these different realms. So we'll enter out into the field, collect data here to establish a rating equation, and then we'll also do the same thing with a physical model in our laboratory, in our WEIR, and then also using computational fluid dynamics. And so there are a few different instruments we have to be able to non-intrusively measure what the velocity field is doing within the laboratory, which is very important, going back to the point I mentioned earlier on limiting the intrusivity of our measurement, which is two pretty well-known techniques, which is PIV, particle image velocimetry, and then LDA, laser Doppler anemometry. And I just have a few graphics here to show so what our setup is here. So we've modeled one of the just a sharp crusted weir here, and we have some paste to limit seepage along the sidewalls. But this is the laser Doppler anemometer here measuring. So this is a point measurement, and we go up and down through the depth of the flow in order to establish a velocity profile at multiple different distances from the weir. And then similarly, we can also take PIV data. This is a similar setup where we have the weir on the left here, so it's just inverted. And the neat thing about the PIV is we can actually establish a two-dimensional velocity field, and we can do a lot of really interesting statistics, second-order statistics with the vorticity and the divergence of this velocity field as it decelerates and travels over the weir. So our current status of this project, we've been hamstrung a little bit, obviously, with the COVID-19 situation, but we were able to get a PIV system set up in our lab in about August of this year, of 2019. And what we've done since then is we've had to establish some optimization procedures for how to best collect data using the PIV instrument. So that's sort of getting at how to analyze the turbulent signal of the velocity field, how long to measure, when to measure, what's the total number of sort of images that's necessary to establish a robust mean profile. And then the first sort of venture into modeling hydraulic structures that we'll do is modeling what's called a pivot weir or an Obermeyer weir, which are found in the nearby Larimer Well Canal in Colorado. So this will be building off some work from Channer Kutlu, who published his thesis in 2019 on the rating equations for these structures. And then along with that, we've had some interesting time fine-tuning the CFD software to synchronize the results from our laboratory data with the computational fluid dynamics data using Flow3D. And just quickly here before I wrap this up, we've just started to take a few different trials of experimental data from our lab. And one interesting thing that we found is sort of a drawback in our velocity profile at near the free surface, which shows that there might be some sidewall effects in our narrow flume. So the flume that we're currently using is only 300 millimeters wide, and we're operating at the depths of our flow anywhere from 10 to 20 centimeters. So a lot of the irrigation canals we're working in could be considered narrow channels, and so what we'll continue to look into is if this drawback effect due to the sidewall is also present in the irrigation canals we'll examine in the field coming out as we're able to into the spring and the summer, and this will help us sort of further optimize our ADCP measurement techniques, because there'll need to be a correction factor for any sidewall effects when measuring in a narrow irrigation canal, which currently isn't used. It's generally the manner in which ADCP measurements are made is sometimes standardized anywhere from an irrigation canal that's 10 meters wide to a river that's hundreds of meters wide. So that's about all I've got here. I think I'm just a little bit over time.